Hey, I'm Dr. Robert Eckel from the University of Colorado Anschutz Medical Campus in Aurora, Colorado, and also one of the co-chairs of the Cardiometabolic Health Congress. And with me here is Dr. Alan Chait, who's the Bierman Professor of Medicine, former division head of endocrinology and metabolism at the University of Washington. And Alan, we're here to talk about your keynote address here this morning that related to mouse models of inflammation. So can you expand that a little bit in terms of what you addressed with the audience and its relevance to inflammation in humans and metabolic syndrome?
So the advantage of studying mouse models, Bob, is that we can access tissues which are not available to easily accessible in humans. Examples being visceral fat, which we can easily access in mice, and arterial tissue, which again we can access in mice. You can only get it post-mortem or post-surgically in humans, and therefore we can study mechanisms that are pertinent to human disease. Particularly the mechanisms are what we can study in mice, and that really help us understand human disease, and we can then use this in a translational sense to make advances in therapeutics and diagnostics in humans.
So one of the big issues in the metabolic syndrome that clinicians are concerned about is the modification of lipid levels, and particularly low HDL cholesterol is probably the most common abnormality in obesity per se, but then you get into more extended paradigms of insulin resistance. That low HDL cholesterol not only is low, but it doesn't work very well. So how does your mouse model help us understand what may be going wrong with HDL? Keep in mind, clinicians measure HDL cholesterol, not HDL function, and how do your mouse studies help us there?
That's the real issue. HDL cholesterol is a poor metric. As you know from many of the intervention studies, particularly the pharmacological intervention studies, the HDL cholesterol has led us astray. It really hasn't helped us. So the question then becomes, is HDL functional? Is there something wrong with it? And this is where the animal studies have truly helped us. What we have discovered and now know is that when HDL acquires serum amyloid A, SAA, as a particle that is transported in the HDL particle, then it really becomes dysfunctional. And we now have, as a result of studies in animals, we have a lot of insight into why it is dysfunctional, both at the level of adipose tissue and at the artery wall.
Now, SAA is really the mouse C-reactive protein,
correct? That's correct, yeah, sure.
And why visceral fat rather than subcutaneous fat? Do you understand mechanisms that relate to why that depot seems to be predilected to inflammation and perhaps systemic effects?
Not well, but we do know that there is a big difference in the biology of visceral versus subcutaneous fat. And even if one is overweight subcutaneously, it may not look good, but it's much less dangerous than if you're not even particularly overweight, but have an accumulation of intra-abdominal, also visceral fat. This is associated with cardiovascular risk factors. Exactly why this is so is not known, but the beauty of studying animal models is you can access the visceral fat, you can access the subcutaneous fat, and compare the biology and the mechanisms in these two depots.
Talked a little bit about the M1 and the M2 macrophage, and I think that same kind of biology exists in the central nervous system with M1 and M2 microglia. Yes. How do these types of macrophages differ and how they relate to adipose tissue metabolism and inflammation?
Yeah, well, the M1 macrophage, it's an oversimplification, but let's for simplicity's sake call it an M1 macrophage. This is a macrophage that accumulates in adipose tissue in expanding fat adipose tissue during times of inflammation. It's pro-inflammatory, it can lead to insulin resistance, and it's an adverse type of, it's a bad type of macrophage to have accumulate. Conversely, the M2 macrophage is a less it's an anti-inflammatory,
a
clean-up cell.
Right.
It's there. It's really there in a clean-up mode. And the more, if you're going to have macrophages in your adipose tissue, or in your artery wall, or in your brain, clearly it would be nice to have the M2 type of macrophage there, because this is a macrophage that's really doing good, more good than harm.
And here I think your data in the mouse really reflects the types of macrophages that are in human adipose tissue too. Correct. This whole issue of the healthy obese state. Would those people who have healthy obesity have more M2 macrophages or very few macrophages in general? Do we know that?
Fewer macrophages, but what macrophages there would tend to be more of the M2 variety.
A lot of your recent work connects your history and atherosclerosis-related research to what's going on in obesity, metabolic syndrome, insulin resistance, and that's in the proteoglycan story. Could you evolve on that concept a little bit?
Yeah, this has turned out to be quite interesting. We're really very excited about this at the moment because the biology in the artery wall and the biology in adipose tissue seems to have many similarities. So what we do know from a long history is that in atherosclerosis, proteoglycans produced by the vascular cells in the artery wall, trap lipoproteins and have adverse effects as a result of trapping lipoproteins. What we are now discovering is that a similar biology exists in adipose tissue. When a mouse, and presumably a human, we're now doing it in humans, but we have the data in mice, when a mouse gets fat, it makes certain proteoglycans. The fat cells make certain types of proteoglycans, and the macrophages make a different type of proteoglycans. And these then trap lipoproteins, and particularly SAA containing HDL in adipose tissue, and it prevents HDL, normal HDL, from having its anti-inflammatory effect in adipose tissue. So the biology is probably very similar in artery wall and adipose tissue, which is really quite fascinating and a lot of fun to study.
But the history in terms of cardiovascular disease and atherosclerosis has been that these proteoglycans might preferentially bind lipoproteins and allow them to be retained within the arterial wall. What about other organs that accumulate lipid that relate to insulin resistance, such as the beta cell or cardiac muscle, et cetera?
Or liver.
Or the liver too, yeah. Absolutely.
Well, it's quite possible that similar mechanisms exist in those tissues as well. We haven't studied them, and they haven't been well studied in terms of proteoglycans. There is emerging literature in the pancreatic beta cell that amyloid is involved as well, particularly in type 2 diabetes. So it would not in the long term surprise me at all if the biology was the same in many tissues.
Well, it's a very exciting area because proteoglycans are in every tissue of the body, right?
Oh, yeah.
And so the modification and their binding of pro-inflammatory molecules, et cetera, seems like an exciting place for this field to go that links metabolic diseases to cardiovascular disease.
That's the exciting part to me.
So when a clinician, he or she reads the literature from murine models of human disease, what are the cautionary notes that you recommend that clinicians think about up front to make sure they don't under or overinterpret the data?
Well, the problem is, mice are mice, and oftentimes what you find in mice don't translate straight across to humans. So you've got to have a healthy dose of skepticism when you look at the data. And you then have to say, well, let's do this. What mouse studies really can do is set up important hypotheses and questions that can be tested in humans. They can't do much more than that. There clearly are differences. I mean, let's take lipoproteins as a classical example. The mice are HDL animals. Humans tend to be more LDL animals. That's basically very different. So to study lipoproteins in mice, you have to use genetically modified mice to model the human lipoprotein profile. And so that's a clear-cut example. Another example might be the fact that in therapeutic advances in humans don't necessarily are the same as in mice. For example, statins work very nicely in humans, don't work nicely in mice. So these are just two examples where there's a major difference between the two. So you need to look at the mouse studies with a healthy dose of skepticism, but they really have helped in trying to ask important questions in human biology.
Right, I think Dr. Chait has really summarized very importantly how the clinician should look at preclinical models of either drug treatment and or disease mechanisms, but also don't ignore the fact that mice aren't humans. There can be important insights in terms of mechanisms that come from these murine models of human disease. So I want to thank Dr. Chait for joining me here today, following a very exciting presentation as a keynote speaker here at our meeting in Las Vegas, Nevada. Thank you very much, Alan.
Thank you, Bob.